Hello, welcome to Huck Circuits. Today we'll be talking about a circuit where two resistors are connected in series. When two resistors are connected in series, or when any two components are connected in series, that means that current only has one direction to flow and cannot go anywhere else. So you can see here that current comes out of the voltage source and it flows in a circle right back to the voltage source. And as it's traveling, it goes through both of these resistors and the current cannot travel anywhere else. For example, if we added another resistor right here, and now the current comes over here. Now when it reaches this junction point right here, the current has two directions to travel. One is that way and the other is that way. Since the current can have two directions to travel, that means it's not in series anymore. So in order to be in series, you cannot have a junction there. So let's get rid of that. Now the current goes just one path and it's in series again. Now to solve this circuit, we need to use Ohm's law, which we know is voltage equals current times resistance. Now let's gather our data first. So V equals, from the circuit diagram, we can see that it is 5 volts. The first resistor is 4 kilo ohms. R2 is 6 kilo ohms. So the way we solve this is that we have two resistors here. And since they're both in series, you can just add up their resistances. So to get the equivalent resistance, we need to sum up these two resistors, which means that R equivalent equals R1 plus R2, which gives us 4 kilo ohms plus 6 kilo ohms equals 10 kilo ohms. Okay, now we'll now take our Ohm's law and we'll go voltage over resistance equals 5 over 10,000 ohms equals and we get 0.0005 amps. Or 5.5 milliamps. So we got the current right here, I1, which is 0.5 milliamps. Now let's say we want to know how much voltage is dropped across resistor R1, and also again how much voltage is dropped across resistor R2. We can do that again by using Ohm's law. V equals IR. So let's say the voltage across R1 equals, so we know that current is 0.5 milliamps, but we'll convert that back to amps. So there's 3 zeros, 5 times 4,000, and the voltage across R2 equals, again we have our current times 6,000 ohms. Okay, now we set up our problem to solve here. So R1 or V, the voltage across R1 is 2 volts. And our voltage across R2 is 3 volts. So if you take a look here, you have 2 volts across this area here. So there's a 2 volt drop here. Let's actually draw that into our diagram. So right here, when you go the plus and the minus, because it's a voltage drop, the voltage drop of VR1 equals 2 volts. So there's a 2 volt drop across this resistor, and across this resistor we know that there is a 3 volt drop, 3 volts. So now you can see that we start out with a 5 volt source, and as we travel, first we drop 2 volts here, and then we drop 3 volts here. That's a total of 5 volts. So the source is giving 5 volts, and the drops across both the resistors sum up to 5 volts. So it's a balanced system. And if we want to go ahead now and just get the power across each component, let's go ahead and try that. See what we get. So when we deal with resistors, so the power across resistor R1 equals, the magic formula is the current squared times the resistance equals 0.1235 times 4,000. And the power across resistor 2 equals I squared R2 equals okay, let's see what we get here. So the power across resistor R1 is 0.001 watts, or 1 milliwatt. Now across R2, I forgot to square it right there, squared times 6,000 equals 0.0015 watts, or 1.5 milliwatts. Let me just backtrack a little bit and make sure I did the first power equation right. So 0.005 squared times 4,000. Yes, we did that correctly. Okay, now we want to know the power across the source. So the power across the voltage source equals negative voltage times current, which equals the negative sign. Voltage is 5, and the current is 0.1235 equals negative 5 times 0. Negative 0.1225 watts, or negative 2.5 milliwatts. So what that is saying is the input power, like the power coming from the source, and the power which is being dissipated. So I'll just say P dis or P out, I suppose, because it's the power going out of the system. And the power, when it leaves the system, it leaves as heat. To explain that, we have a voltage source here, and when the current travels this way, it's going from a negative potential to a positive potential. And depending on how you set up your conventions, kind of determines like whether it's going to be positive or negative. For me, I'm saying that when you go from negative to positive, it's a negative voltage drop. And then when you go from like right here, when you go from a positive to a negative, that's a positive voltage drop. So in this convention, this is a negative voltage drop, which you can see right here is a negative 2.5 milliwatts. So that is negative 2.5 milliwatts equals positive 1 milliwatt plus 1.5 milliwatt, which we know is 2.5 milliwatts. So the power going into the system is the same as the power being dissipated from the system. The word, again, dissipated, just means that when the current goes through this resistor here, that means that the current is being turned into a voltage, and also that energy is being used up as it comes. A resistor kind of resists the flow of current. So as the current is going here, it kind of has to battle to get across to this side here. And how hard it battles depends on how strong the resistance is, where we have 4,000 here. Obviously, this one here is 6,000, so the current's going to fight even harder to get through this resistor. And when it fights harder, it'll have a higher voltage drop, and also it dissipates more power. And you can see that right here that it's a higher voltage drop compared to resistor R1. But when the voltage does go, when the current does go through here, there is power which is being left, it leaves the system as heat. So you can kind of like imagine, these lines here, just like heat is being generated. Ideally, we just say heat is leaving. That explains, and it really does explain what happens to the energy of the system. It just leaves as heat. But in real life, if you like design this in a lab, and depending on how much current is going through this resistor, if you go past what the component is rated for, like if this can only handle a certain amount of current or something, this resistor, you could blow up the resistor if it's dissipating too much power. Like if it gets too hot, it'll break because it's a real life component and not just an ideal component such as how we drew on this paper here. But that is the lesson for today, that the power into the system is the power out of the system, and the voltage, the total voltage of the source equals the total voltage drops. This will always happen. And this is also something that we call, when you go around this circle, is Kirchhoff's voltage law. Let me just add that down here. KVL. And KVL just says that when you go around in a loop, the total sum should be 0. So if you have like a -5, all this here should also equal 5 volts. And that's what's happening here. So thank you for tuning in, and please come back again for the next lecture.